So let's do a calculation for the energy for ion pair formation between the potassium and bromide ions from their elements in the gas phase. So what is the energy for this process? Which of course requires that we ionize the potassium and the bromide, so we form K plus and Br minus, and then bring those ion pairs together. And we're going to sum up the energies required for those three steps to get the total energy for the ion pair formation. I'm going to provide a diagram too that's going to help sort of illustrate what's going on in the process. We're just going to do a qualitative scale of energy increasing as you go up on the y-axis. We'll start with the gaseous atoms of potassium and bromine, of course neutral charge, and the line here just represents the sort of relative energy for these two as the reactants. Now we're expecting that in order to remove an electron from potassium and add an electron to bromine, that the sum of those two steps is going to require a little bit of energy input on our part. In other words, our energy for that step will be positive and result in a higher energy state for the potassium plus and bromide minus. Like so. Now, if you weren't sure that would be the case, you can do the calculation first. And we'll see that in order to ionize potassium, we have to remove an electron from the neutral potassium elemental potassium atom in the gas phase to produce K plus an electron. And of course we know that the energy required for this process is called the ionization energy. In this case, that is going to be a positive number with a value of 0.696 attajoules. And this is simply, you find this is going to be tabulated for you, and you can find it in your text or other library or online resources, 0.696 attajoules. And notice that the number is positive. It's a positive number, and that's because it always requires energy to remove an electron from the attractive force that's holding it to the atom. In other words, the attractive force between the negative charge of the electron and the positive charge of the nucleus on the potassium. So that requires energy input, and therefore so whenever we have to input energy, we're going to write that as a positive value. Now the energy that is, in this case, given off when we add an electron to the bromine to produce bromide minus, which is called the electron affinity, is 0.540 attajoules. And this also is going to be found in tables of data. I looked this up and wrote it in here. And for the problems that you'll do, you'll also be looking to those tables of data to find that value. So ionization energy, electron affinity will be given to you, and I found 0.540. In this case, the electron affinity, though, is going to be negative value. And the first electron affinity is usually negative. In other words, this electron wants to be associated with that atom, because the atom has a positively charged nucleus, with the protons in there, and of course there's a strong force of attraction between the positive protons and the negative electron. Keep in mind, in the previous movie we stated that when you add additional electrons in, electron affinity number 2, electron affinity number 3 tend to be positive because of the repulsive force between the negatively charged electron and the negative charge on the anions that you're adding those electrons to. So in other words, if I add an electron to Br minus to make Br2 minus, for instance, well, for one thing, that's going to require, that's going to be a weakly held electron anyway, because it's going to be going into a new and larger shell. But in addition, I'd have to add the electron to a already negatively charged anion, and there's some repulsive forces then that we have to overcome. Okay, so anyway, we're at the point now where we know the energies for forming these ions that we need, and if we add these two up, we'll get the energy that it required, the input energy required to form those two anions. So we add those up, and we get 0.156. That's positive, so our up arrow is correct here, and therefore we have positive 0.156 attijoules required to produce our K plus and Br minus. In the next step, we're going to take those ions and bring them together, right, to form the ion pair, and the energy that we get out of that process, and that's usually going to be an attractive force, and therefore we'll show that as a negative energy value. In other words, we get energy back from that, from bringing those together. That is calculated by Coulomb's law. Okay, that is going to be, as we said, negative. We're going to get energy back. We're going to calculate just how much energy we get from that third step. Okay, and Coulomb's law, as you recall, is this, where d is the distance between the ions, which is calculated from the radius of the cation plus the radius of the anion. Q1 and Q2 are the charges on the cation and the anion, and K is a proportionality constant, which is given, and in this case has units of attijoule picometers. Now, energy then for this attractive force is equal to 231 attijoule picometers times the charges of the cations. In this case, we have +1 and -1, so we substitute those into the equation here, divided by the radius of the cation. I look up into a table of data in my textbook or some other online resource, is 138 picometers. That's for K plus. The radius of bromide is 196 picometers. You can also find that in your textbook or in another resource. Adding those together gives me the distance, the separation distance between those two ions. And then taking this calculation through, I get negative 0.6916 or 0.692 attajoules. Notice the picometers cancels out and leaves me with units of attajoules, energy unit, which is good. And now I can put that into my diagram, negative 0.692. So I know that I had a drop in energy of 0.692. I get that much energy back for that step. The last step then is to then sum these to get the energy for the ion pair formation from the elements. In other words, the energy for this reaction, which is what we were looking for. And that is represented by the red arrow going down. And I'm simply going to add the energy for the ion pair formation being equal to 0.156, the energy required to ionize and then the energy force of attraction between those ions, add those to get 0.536 attajoules. And that is the energy for the reaction shown here.